thank you for the organizers to inviting me to talk today about something I've done in collaborations with Noé, Cuneo, and Volkan Jaksic, Jan Pautrat, and Pillet. So it was published this year. Interesting is this hypothesis testing. So it fits in the thematic as like an estimation thematic of the of this workshop. And particularly, I will illustrate our results on something that motivated us initially is the question of emergence of the arrow of time in repeated quantum measurements. So what I will talk about when I talk about emergence of the arrow of time is typically the difference between these two movies here. So in each movie here is played first forward and then backward and again. And you can see that on the left here, it's, okay, I don't know, you can maybe have a show of hand, but it may be hard to guess when is the movie played forward and when it is played backward. So there's actually an hint, but it's very hard to see. Whereas here, it's very simple to see it. Like you know instinctively when is the movie played forward instead of backward. And this is due to just the difference between microscopic reversibility of the laws of physics versus the irreversibility of the second law of thermodynamics. So this is just this difference here that, that gives us the ability to, this is this second case here where we can typically know that when the movie is played forward or backward. Or as one of the first statements about this irreversibility is just that it flows from the hot to the cold path. So what I will talk about when I talk about emergence of the arrow of time is not actually, we could ask whether when can we know if it goes forward or backward. I won't talk about the transition from the microscopic reversibility to the macroscopic irreversibility, but more quantify the macroscopic situation where I want to try to understand how we can infer the movie order in the second case, from the second law. So this I will use to decipher this meaning using basically what seems more appropriate in statistics is just hypothesis testing. And why I will do it on repeated quantum measurements is typically that it becomes nowadays more and more experimentally relevant. We'll show an example of experiments where they actually do repeated measurements. It somehow more corresponds more to everyday experience than the usual definitions of entropy production and things like that in quantum mechanics. And also, and because I'm more of a mathematician and nowadays more and more mathematicians and a physicist, it's because I can have results and I'm happy when I can have actual analytical results and not only numerical results. So today I will talk about, so first what we mean and how do we formulate repeated measurement models. I will talk about this identifiability of what is called the instruments and the relationship with relative entropy, and finish with this hypothesis testing and particularly what is more interesting in the hypothesis testing is the error exponents of hypothesis testing and the construction of best test or strategy of choice of the arrow of time or two different instruments. So what is typically an experiment of repeated measurements is the well-known, and I guess everyone here has heard this, has seen this image at least once, is Serge Haroche group's experiment, which became famous in 2012. It's just so electromagnetic field, so trapped, so for some photons trapped in superconducting cavity. And some atoms, idealized as two-level systems, are prepared here in a given state, fly through the cavity and interact with the electromagnetic field, and are then measured. So the result of the experiment is what? Is a sequence of measurement results, like state preparation and measurement results. And from that, they can infer the state of the cavity here. And particularly, one of the huge achievements was to measure and fix the number of photons inside the cavity without destroying them. Another experiment which would be closer to this idea of flow from hot bath to cold bath is this one. So you have two baths, one in red here, which would be typically the hot bath, and blue. It's seen as reservoirs of particles. And we have a system here, which is described by the density matrix. And what can happen is that with probability, equiprobability, an atom will come out of the hot or cold bath in a state corresponding to the temperature in either of these baths. We'll measure first the energy of the atom coming out of the bath, let it interact with the system. Here with this specific interaction, it's actually kind of important here, but you can use anything you want, of course. Measure the energy after the interaction with the system to see the variation of energy. And then what we obtain is an updated state of the system, given the bath it came from and the two measurement results. And we can repeat that. So next time, for example, it comes out of the cold bath, we have a new initial energy. We let it interact, a new final energy, and we update again the state we had before. And then it depends on 6 indices. And you see that the evolution depends only on these matrices here and the difference of energy. And if we repeat that many times, the actual distribution of the data we obtain is given just by products of such matrices where we summarize the 3 indices into one letter. So this is typically a 2-time measurement picture in repeated interaction systems. So this was studied particularly by Crooks in 2008 and Horowitz and Parondo in 2013. So more generally, so this is 2 examples of repeated measurements, but more generally we can formalize what will be repeated measurements in general case. So what we always have is that a system, which is density matrix, so infinite dimensions. We have some maps which are important, which are completely positive maps, which is basically are maps that can be written like that with VK taken in a family of matrices. And the average evolution, without taking into account the measurement results, is given by what's called the quantum channel. So a quantum channel is just a map written like that, but that would preserve the trace of any density matrix. And so the average evolution is just given by a repeated application of this completely positive, this quantum channel. Now, if we take into account the measurements, we have to decompose actually this quantum channel into an instrument. So an instrument is just a collection of this completely positive map indexed by the measurement results, here K. So that's the sum, okay, we recover the completely positive quantum channel. So what it means that K here, the index on the instrument, is just, it encodes what is the measurement results we observe. And phi K corresponds to the action and the effective evolution of the system given the measurement outcome, K. And it's just updated, like everything from, the state is just updated in this way. And it of course becomes a random variable due to just the laws of quantum mechanics. There is nothing new, nothing different than all the laws of quantum mechanics here. This is just a general formulation of repeated measurements. So the unraveling, what I will call unraveling here, is just what is the distribution of the measurement outcomes you obtain from this instrument and density matrix here. So this is really the distribution of the data we will obtain in our experiment. So there are two properties that are interesting to us. Is that first an ergodic property. The ergodic property is just saying that if you look at the probability to obtain a measurement result at the beginning of your experiment and another one very late after that, they basically become independent. This is the meaning of this here, of this limit here. And this is true as soon as you have like your average evolution of your system as a unique stationary state. Meaning like you stay in the, you basically will reach, starting from any state, you will reach, in average, always the same state. And the other property you have is that this what we call quasi-upper Bernoulli property, which is just mathematical properties of submultiplicativity of your probabilities, which is just basically technical, but which will become like very important in our study. So what in this context, so this is some model here when I define it. Sorry. So when I define these probability measures, it's just a model. And what I will be interested in is the hypothesis testing for the formulating and studying the hypothesis testing for such kind of model. So what we mean by that is that we have these movies of the experiments, and basically we have a movie, and it can come from two different instruments, either the J or the J hat. And we have so we have to distinguish between the two possibilities of these instruments, and we want to know how if we can do it, and how can we do it efficiently. So we formulate it by usual formulation of hypothesis testing. So we have a null hypothesis, which is just saying that what I observe of my experiments are given by an instrument J and a state rho. And the alternative hypothesis is just that the observed quantum measurements are described by J hat and rho hat. I will not refer now to J and rho because they are kind of irrelevant in our results. So I will just talk about J and J hat. So but this does not actually correspond really to hypothesis testing of the arrow of time, because you see that in the arrow of time we didn't have two instruments. We just had two directions of the movie. But actually it can be reformulated also using instruments. So in the arrow of time, what we have is that what we will do when we compare the movie forward and backwards, that we will typically take the last, when we reverse the movie, we take the last frame of the movie, we reverse all the momentums. So we apply this theta k here to reverse all the momentum, and then we revert also completely the order of the frames of the movie. So this is this reversal here, that here, each k is a frame of my movie. When I reverse it, in each frame I reverse the momentums, and I reverse also the order of my frame, and my last frame becomes my first, and my first frame becomes my last. So the probability to see the reverse sequence is just given by the initial probability. So, sorry. If I'm shown the movie backward, it's just saying that I have my initial probability, but with the sequence reversed. So we have two hypotheses here. If we are watching the movie in the recorded order, what we expect as the distribution of the outcomes, of the frames of the movie, is just given by this P, the forward distribution. So this will be our null hypothesis. If we watch the movie in the reverse order, what we expect as the distribution of the outcomes is the reverse distribution, so the backward distribution, which corresponds to our alternative hypothesis. And actually, we can also, this hypothesis testing, we can reformulate it in terms of testing of instruments. Because given a forward instrument and a local involution, this reversing of the momentums, we can always construct an instrument corresponding to, which will give us the reverse probability. And an example of such instrument is this one here. So actually, the testing of the arrow of time can also be seen, hypothesis testing of the arrow of time can also be seen as a special case of testing between two instruments. So basically, I will present the results of testing between two instruments in general, but keep in mind this idea that it is best fitted to test the direction of the arrow of time in the meaning I said, I told you about at the beginning.
So this is a physical instrument? I mean,
this one, okay, you can have also physical instruments, like reversing microscopically the time, but it's not always this one. It can be an equivalent one, but it can be this one sometimes. It depends. But this one will work, but it's not the only one. You can have many others. And actually, you can have some results about how many others you have. Okay, so typically if I look at, and here will be an example of a physical reversal typically. So if I look at my 2-bass example, we have the reversed evolution that I may expect to see is just the opposite. That I have my atom coming from my hot bass. I first measure what was initially my last measurement. I let it interact, but with the time going backward. So I take the conjugate of my unitary evolution to when it interacts with the system. I measure again, but this time I get the initial measurement. So the result is that a variation of energy, which is positive, becomes negative. So I invert all the signs of the exchange of energy, which corresponds to permuting between I and J here in my theta. So reversing the momentum corresponds to reversing the signs of the energy exchange. And I can repeat again, and I will have this. This is the reversal. And this you can derive it microscopically directly from the reversal of time. So to study such the reversal, what we will look at, and knowing a bit of either of hypothesis testing or actually thermodynamics will not be surprising, that what we will look at is the likelihood ratio. To distinguish between the two hypotheses, we will look at the likelihood ratio between the two hypotheses here. So we'll look at it, its log in mean, which is just the relative entropy between the two probability measures, and as a random variable, which corresponds to a rate, or what I will call in this context the entropy rate, entropy production rate. And for the arrow of time, we have a symmetry, but it's not true in general. What is important, and so what will be important for us about this quantity is what are the behavior when you have more and more data. This is what is interesting to you when you are doing hypothesis testing. Because when you have your movie that is longer and longer, you expect that you will know better if it goes forward or backward. And we'll use this submultiplicative, this upper Quasi-Bernoulli property where I talked about, to actually use some standard results of subadditivity, convergence of subadditivity in mathematics, so that we can prove, that actually the entropy production, like the mean relative entropy, converges towards the quantity I call entropy production here. But not only in mean, but also almost surely, so with probability 1. But more than this result, we have that if the limit here is 0, it's equivalent, the fact that this limit here is 0 is equivalent to the fact that the forward and backward measures, so the two hypotheses you are testing, are actually equal. And the distribution are actually equal. Which means somehow that you expect that looking at the sign of this quantity sigma here will tell you what is the right probability measure describing your experiment. What is the right instrument describing your experiment. So this is this idea that if I'm looking at all my measurement results, I compute this entropy production rate. If I see that it's strictly positive, then it's a forward instrument that describes my experiment. If it's strictly negative, I know that it's actually the movie is shown backward. And if it's 0, the only thing I can tell is that I cannot say what is the right order of the movie. And just a remark that you see that actually here the condition is on the distribution, so we have a question that is actually kind of still open about what is actually identifiable on the instruments. They are actually identifiable only on a subset, and there is of the density matrices, and there is some work to be done to understand when it actually is identifiable on the full set of density matrices. So what does it correspond to in our example related where you can easily understand the thermodynamics? But simply, the entropy production, as I defined, corresponds actually to the classical definition that we have a sum of the variation of heat in both reservoirs weighted by the inverse temperature. And we have the convergence with probability 1 of the current of heat from the hot to the cold bath. The entropy production is strictly positive, implies that the sign of the current corresponds to the sign of the difference between the hot and cold temperature. So we have a really current from the hot to the cold bath. Moreover, we have that if the entropy production is 0, then the entropy production is 0, if and only if the two temperatures are equal, and if and only if also we have no current between the two baths. And this is true for the Hamiltonian I'll talk to you about, like this full dipolar interaction between the two level systems. If I take another interaction, typically an XX interaction, I will have always a strictly positive entropy production. And that's because by switching on and off the interaction, I will add always some work into my system. Okay, so we have some limit results, but actually we would like to understand better how we can decide, because basically in an experiment, you cannot wait until the end of times, until you have infinitely many measurement results to say, okay, sigma is strictly positive or not. So we want to understand how the error of guessing what is the right order of the movie behaves. So typically we need to define an event, so something that will happen in our experiments so that when we see it, we say, okay, the movie is shown to me in the forward time, in the order it was recorded. And this will be this event T, and typically it can be that when I see that the entropy production is strictly positive, I decide that my null hypothesis is true. And there is two possible errors, kind of errors. Either we have a false negative, so we reject our null hypothesis when it is true, or we have a false positive, meaning that we accept the null hypothesis when actually so we decide that the movie is played forward to us when it was played backward. And we want to quantify, so we want to quantify the decay of these probabilities of error. And the first result is is a Stein error exponent. So the first, it characterizes decay, sorry. It's characterized by some error exponents that characterize the decay of errors. And the first one is, ones are Stein error exponents, which basically characterize the minimal false positive probability when you control the false negative probability. So you fix a maximal false negative probability here, which is upper bounded by this epsilon, and you look at how the false positive error behaves when t goes to infinity. And actually, what you can, from the result of our convergence of the entropy production, you can directly show that whatever is the value of epsilon, so however you control your probability of false positive, of false negative, sorry, the probability of false negative, the minimal probability of false positive, is decaying as with a rate exponentially fast with the rate corresponding to the entropy production. Yeah. And what is interesting here is that actually the proof of this result is constructive, meaning that here you construct a set of tests that are good, meaning that they will saturate this limit, and you know that you cannot construct a sequence of tests that will be better than this one. You can find equivalent ones that will be maybe more suited to your experiments, that will behave better at the beginning, but asymptotically, this test will be optimal and you cannot find better ones. But so here you define a probability like you control uniformly in time this probability of error, but what you want is to better control. Either you want to control better the decay of probability of false negative, meaning that you don't want just it to be fixed, but you want it to decay fast enough. Or you want to just don't care about the false negative, false positive, you want just that your total error decays fast enough. So you want to see how it happens. And for that, we need to study, we'll go through studying the cumulant generating function of the entropy production, which is just Renyi relative entropy. So for the hypothesis testing of the arrow of time, one thing which is interesting is that you see directly actually that the cumulant generating function of the entropy production, so the Renyi relative entropy, is actually has a symmetry corresponding to transient fluctuation relations, so that you have it always. And then using this quasi-upper boundary property I talked to you about, that you have automatically in repeated quantum measurements, you have this subadditivity of your Renyi relative entropy, so you can have directly by effect lemma the convergence of your relative Renyi entropy for the orders between 0 and 1. So you also have that the derivative in 0 and 1 given by the entropy production. And for the time arrow hypothesis testing, you have also the evidential symmetry, so the symmetry corresponding to fluctuation relations. And this limit is actually what is interesting, that more from a mathematical point of view, is that actually you can obtain this limit E of alpha as through a variational study of some equivalent of free energy, meaning that you use some maximization of some free energy or entropic pressure as for equilibrium states and Gibbs states, but here for out of equilibrium situation. But I won't go too long on that. And okay, so if we add, the issue is that here, if you look at, we have some regularity of this Renyi relative entropy, depending on alpha. We know that it's continuous, but we don't have differentiability, and this actually is important to be able to apply some result of large deviation. And this, we need another hypothesis, which is harder to check. But if we, under this hypothesis, we obtain that E of alpha is differentiable on 0, 1. And this is sufficient, and this is done. So if to have some new results on the hypothesis testing I was talking about before, typically you have, you can characterize as for Stein exponent, you can do the same thing, but asking now not for controlling just the probability of false negative, but just to control the decay of the probability of false positive. Of false positive, sorry. So here it's characterized by what are called Hofding's exponents. And you can show, basically using our results, that all the Hofding's exponents here are equal. So it means that and the proof is again constructive using Neyman-Pearson tests. And basically that using large deviation results, you can construct a sequence of tests such that the probability, you control the decay of probability of false negative is decaying as with rate S, and the decay of false positive is decaying with rate HS. And you know that you cannot construct other tests that will decay faster than that. And so this is for the decay, and for the total error exponents, is just Chernoff error exponent. So if you look at the total, if you assume a key probability between your two hypotheses initially, so your total probability of error is just a weighted sum of the two probability of error. You have like an explicit test that minimizes this, this probability of error. And we can show that you have and the decay of this error is characterized by these two exponents, which is just a lim sup and lim inf. And we can show that this probability error decays with a rate which is given by the minimum of the Renyi relative entropy. So it's a lot of results from that may be a bit hard to follow, but we can summarize them by on this picture. So this is just where I just plotted the Renyi relative entropy of this example with the two bars presented to you. And so here, depending on alpha, you have E of alpha, and for the different curves corresponds to different difference of temperature. And the gray lines are just derivatives. They are fine lines corresponding to derivative in 0 here and 1 here. So this is the slope here is given by the entropy production here also. And you can see that you have like the Chernoff error is given by this difference. So as the temperature goes down, the temperature difference grows. The probability of error decays faster. And same thing for the entropy production. Okay, I'll go faster. So it's a collection of results, and what we tested after. So we have like a full theory of the hypothesis testing of these repeated measurements. That we know that we have the basic results of the error exponents that we can derive always in that case, and this is actually not usual because the only other cases where you can easily find these are typically simple Markov chains or IID cases. Here we are not in that case. We don't have explicit Markov chain. We don't have on the Markov chain that is related to this repeated measurement are not trivial at all, and it's not IID case where everything is trivial. And actually, a sign that there is some deeper structure, mathematical structure behind this result and beyond this first result is that we can cook up some examples. So here it's, I won't detail it because I only have a few minutes. But this is an example where actually what you can show is that all our hypotheses and results hold. And also the probability measure it does not fall into a usual family that we study in physics, so typically Gibbs measure. It's not a weakly Gibbs measure. we have that E of alpha exists everywhere, but is not twice differentiable in 0 and 1. It's analytic everywhere else. And what is interesting is the entropy production does not follow a standard central limit theorem. The central limit is not a Gaussian. It's a Gaussian plus the absolute value of another Gaussian. So there is some reminiscence here of some kind of phase transition, but on the level of the entropy, relative entropy. You have also other examples where you can show actually that for, like you have using a unitary rotation and some transition between different states, you can cook up an instrument so that actually for almost all angle of rotations, E of alpha is finite everywhere and everything works fine. But for a dense set of angle, you have that E of the Renyi relative entropy is actually infinite outside 0, 1. And you have a finite differential in 0. And another set of dense set of angles such that E of alpha is infinite outside of 0, 1, but the derivative is infinite also. So you have these cases where you have, for those who know a bit about large deviation principles, that you have steepness or not, it depends on your parameters. And finally, you can cook up examples using these matrices, such that you have a model where Renyi relative entropy is twice non-differentiable in -2 and 3. So you have somehow, but it's, you expect that it's somehow equivalent to a second-order phase transition at those points. And a case where actually we even have a first-order phase transition, because we have an example with these 3 matrices where actually E of alpha is non-differentiable at some point which is equal to, it should be actually -2, around -2, where it's actually non-differentiable. So this is just these results are like a first look at these models as non-equilibrium models that we can study still with some variational principle, and that's apparently have a rich structure, and we are like continuing with to study such examples. And I thank you for your attention.